talk that Peter gave us and the challenge that happened with innovation. I must say we're right in there now because we're going to peek at the future, and we have a challenge with innovation going in new range. And we hope that this will be helpful to improve the cloud treatment in retrieving sea surface temperature. But we're big user of sea surface temperature in our climate models as well. And perhaps someday we can contribute to more data if that can be useful. But if we can remove some of the cloud, that might be an advantage. So what I'd like to talk to today is give you a peek on the program that is going on in Canada in line with the AOS mission that is being prepared for 2031 or so. There's 3 Canadian instruments, and one of them is the far-infrared radiometer, and that is 8 bands that covers the thermal, the normal thermal, and also 4 bands in the far-infrared. So I'll just explain to you what that can be used for. And move, yeah. We know that cirrus are very extensive over the globe, and we're interested in the very thin cirrus, the one that range from emissivity 0 all the way to 1. And the range, depends critically on crystal size. It's, of course, the amount of water, the optical depth, but crystal size is very, very important in the far infrared in particular. And this is also why we can measure the crystal size with the precision of about 10% or 15% because of the high response in that range. Globally, just an example of coverage of cirrus. It's monthly average. It's very large. Where to cut off? It's an asymptote. It goes from dense cloud to 0. So if we can move a little more into the thin clouds and give correction that can be useful for surface assessment of pollution or sea surface temperature, that would be helpful, we think. Well, region budget, we all know, I'll skip that. And the effect of the far infrared is very important. It's about 70% of the radiation that escapes the Earth in the far infrared cool the atmosphere, enhance the polar vortex, and those motion of cold air interacting with the ocean produce a huge storm, and we see that almost every day. And all the events and atmospheric rivers, tornadoes, all that is controlled by cold air, dynamics of the atmosphere, cold air and warm air. What we here's an example of we're not too sensitive for optical depth and radius size in terms of surface temperature, but of course radiance is, and we have 2 customers in this mission. One is the Canadian group is working more on the nucleation and formation of ice and interaction aerosol cloud and water vapor. And NASA is most interested in the closure experiment and extending also the microphysics. But the closure is to verify spectrally the answer is conform with what the radar, LiDAR, polarimeter, and all the other instruments are seeing. So it's going to be important to have a good sea surface temperature anyway. So in Canada, we have, I mentioned earlier, that we have a lot of lakes, a lot of water, and this affects the modeling at regional scale. So we need to have a very good monitoring of all the body of water temperatures. Now, the other thing is, the long wave in the far infrared. So we've been installing our instrument. The prototype is the far infrared radiometer is TICFIRE. It's close by to ERE. It's what Peter mentioned, the MRE. This is the ERE. It extends 25 microns. And it's side by side at Eureka at 80° north. The reason why we're interested in 80° north in winter at minus 55 or minus 40 degrees C, it's because of the very cold air. That's where the far infrared perform the best. And we want to see from space down and capture the very, very cold the Planck function shift into the far infrared as we go to minus 60 or minus 90. And this is where the far infrared shines. So these are the bands that we're using currently. So the 8.6 was mentioned yesterday as one interesting one for sea surface temperature, but also the 11 micron and 12 micron, they're standard, very similar to IIR or other mission. And what we add is the 18 microns, 21 microns, 28, 53 microns. We can go up to 100 microns, but there's not much use to go beyond that. You can see the single scattering albedo as a function of crystal size. And you see that it swings from 10% emissivity to 90% emissivity for the tiny crystal, but it's very sensitive to the crystal size. There's a temperature dependency that we don't know very much into the far infrared. These are one of the challenge. Now, looking side by side, the FIR and the ERE, you can see both here. The ERE is the dashed line. It's not ARI, it's the extended one. And FIR is the solid line. That's the slow response version. It's a very simplified one. But you can see that over a range of 10 radians of 10 watt per square meter per steradian, the clear sky is flat. This is clear sky here. And you can see the cloud varying. It follows very closely in each channel, the two instruments. What's important in this point here is the signature. Each cloud type, each cloud formation, each structure has a fingerprint. And that fingerprint corresponds to physics in the atmosphere. Now, our idea is to measure that fingerprint at kilometer scale and challenge the model to do the same fingerprint in the same kind of cloud, at least in the statistical sense. So it's the very, very much very constraining mode so that we can only have the right answer for the right physics. And that will be helping to constrain our model, we hope for. So we've been flying in a number of flights, the instrument, looking also from the ground. We did some closure experiment. You can see here the brightness temperature for each channel calculated with the microphysics measure. And also, this is for clear sky. And you can see that it corresponds reasonably well. The plateau is where the aircraft stands for a little while and just measure different altitude. The Polar 6 does not fly very high. It's fly only at 5 kilometers, 4.5 kilometers, unpressurized. So finally, the AOS mission. We have 3 Canadian instruments. Ali and Shaw are limb-looking radiometer that look at aerosols and water vapor. And TICFIRE is the thin ice cloud and far infrared experiment. It's on board the Sky, AOS Sky. It will be with the polarimeter, with the, there'll be a Raman LiDAR, most likely, a radar, also looking at the same scene. So this suite of instruments will really constrain the interaction between aerosol and cloud and water vapor in a way never seen before. The other is the incline. We are not part of the incline, but the incline would be interesting to look at delta T change in convection. So if we can better handle the clouds, perhaps we can improve the correction for the sea surface temperature. It's an example of the Jacobian for and you can see here the transmittance is up here for two atmosphere, and the region where it's most sensitive, band 2, 3, 4 are the standard thermal. We have a 6.3 microns here. And these are the far infrared channel. And you can see that it's slope up. And so we can eliminate the surface and look only at the atmosphere, look at the continuum, look at the effect of the atmosphere at every level, specifically the thin cloud in the cirrus. That's our focus. And it also improved the information content in the upper troposphere and also to some extent near the surface. Here you can see the overlap of shows looking at the limb, so we have very, very tight Jacobian. It's a very high resolution in vertical, and TICFIRE overlap with show, so we can do intercomparison or extension. This is an example of the comparison between CALIOP and TICFIRE with the simulator, looking at a very long orbit, looking at data. Ali overlap also in the low end, because ice crystals are aerosol of ice when they're very tiny. And at the other end, the microwave radiometer takes over and continue to measure here the optical depth. The performance for crystal size is very good at small n, because we have a large sensitivity due to refractive index. It degrades a little bit, but still reasonably good. And then the radiometer takes over. What's innovative in this AOS mission is that we will have a polarimeter that will look up to 60 angle. We have, whoops, sorry. We have TICFIRE with 8 bands and extending in the far infrared, and the microwave radiometer also with about 8-9 bands, looking deeper in the clouds. So in the same platform, we have the whole spectrum covered in several bands, from visible to the microwave. Okay. So we have a simulator that is our toy to experiment with the instruments. We start with detailed atmosphere produced by the model or observed by and used also by EarthCare. And we pass it to the radiative transfer engine. And then we have an instrument simulator. This is more engineering with the optic sensor. We use microbolometer in our case, so it's ambient temperature. And we then produce level 1 data and level 2 data eventually. And then we compare these with the start, so have end-to-end simulation. And then we can help the industry to make some compromise into their design. So here is the example of one cross-section where you have AMPS in orange and Calypso in blue. And you can see from pole to equator the interaction between the two at the tropopause, around the tropopause. And the typical accuracy is about 0.25 watt per meter square per steradian for this orbit as a test. And if we look at the amplitude, you can see it's about the thickness of this line here. For different type of clouds, we can measure the properties. And here's the spectral signature between each band from B1 to B8. Again, there's a lot of amplitude, and we can. The next step will be well, we've done a flight in last October, November, December with the AR2, which show on board and Ali. TICFIRE was not present. It's for the next round. It's being designed at the moment. So this is one. And very recently, we had the flight of the launch of EarthCare. I've been working on the team with EarthCare for a good 12 years. And PreFire is also with Tristan, a good colleague. It's also in the far infrared. It's two small satellites, and they're really precursor to what we're going to do. Actually, EarthCare is the second generation. Before we had the A-Train, which is the with CloudSat, Calypso, and Polder. And the next third generation will be, we hope, the AOS HAWC mission with the innovative technology that we mentioned. So that's what I conclude my presentation. I'd be pleased to answer any questions.
Thanks, Jean-Pierre. We have time for a couple of questions. No questions online for the moment. Any questions here in the room?
this is for the future, so I'm sure the custom will come. What we're trying to do now is to design some product that will serve the community. So ahead of time, this is the preparation for the mission is very important because we would like to treat the data here at UQAM for our instruments and also make products that will suit the community well in advance.
Thank you so much,
Thank you.
Jean-Pierre. So our next speaker is online. It should be Chongyuan Mao from the Met Office.
Hello.
Hello, we can hear you.
Oh, great. Okay, so I'm going to share my presentation. Oh, okay. Let's go to the top. Go. Okay, and if I do this, is
Perfect.
it playing? Okay, great.
Yeah.
Right. So, hello everybody. I'm Chongyuan Mao from the Met Office. Sorry, can't be with you in person in Canada. So today I'm going to present to you the updates of the GRIS multi-product ensemble, which is also known as GMPE. Hold on. Oh, it's not moving. Oh, here we go. So brief introduction of GMPE for those of you who might not know the product. So it is a product that produces a medium using participating L4 analyses. And we also provide validation of the matchups for the medium as well as each of the L4 analysis in GMPE against Argo observations. So right now in GMPE, we have 11 products. Most of them are GRIS format. There are a couple of them are not, but we tend to, in the future, just try to add only GMPE products as much as we can. And today in this presentation, I'm going to mainly focusing on potentially adding 3 analyses to the existing 11, which is a mirror 0.25 degree. The full resolution mirror is already in GMPE, so this is another version we're going testing if it's benefiting or not. Another one is NCEI AVHL-OI, and the third one is Odyssey, which is the replacement of Ostia in Copernicus. So we quite like to know how it compares with Ostia. And for the trials, I did 2 pre-operational trials, each 3 months. One is from December 2022 to February 2023, and another one from June to August 2023. And I'm going to show you mainly the results that we typically monitor in GMPE by looking at anomaly to GMPE median, the horizontal gradients, as well as against Argo matchups. The Argo, just to mention, are here sourced from the EN4 products. So first section, just the GMPE, the anomaly to GMPE median, the horizontal gradients. So here I'm only showing these 3 new analyses that we thinking about adding to GMPE. And here we just randomly selected day from the left to right. So you have AVHR-OI, the Odyssey, and the mu 0.25 degree. So just from the glance, they all look sensible, like most differences to GMPE within the 1 degree sort of a bracket. One thing to note is the pattern of the difference seems to be the AVHR-OI seems to be slightly different to the other 2 by showing these kind of bigger patches compared to the other 2 are more kind of not forming patches, but it's kind of more scattering around the globe. But they all look quite sensible. And in terms of horizontal gradients, again, it's what we typically see in L4 analyses where you have higher gradients in regions like west boundary currents region or some regions where we know there is a very fast currents and stuff. So they all look quite fine. And in this slide, I'd like to focus more on the Mao products because we now have the full resolution and the quarter degree. So on the left two panels, on top we have the full resolution, and the bottom we have the quarter degree. So you can see like there are more gray areas in the quarter degree version, which means they probably compare slightly better against GIMP medium, and it tends to be a bit noisier in the full resolution. And in terms of horizontal gradients on the right two panels, or the middle or right panels, you have the full resolution sort of right in the middle and the quarter degree on the right hand side, and it's very clear that the mirror is a lot noisier for the full resolution version than the quarter degree. But we don't actually know that this is a better or worse in terms of more noisy is better or more noise is worse. So it's just like showing you what we see in these plots. And this is very similar to the previous three slides because I'm doing two trials, so I'm just showing randomly one day from each of the trials. So again, you have the anomalies to GIMP median from these three new analyses, and you can see the patchiness in the average OI anomaly against the other two. It's kind of consistent between the two seasons. But again, like the differences are kind of within reasonable degrees. I forgot to mention that the anomalies for the individual OI seems to also have a warmer tone compared to the other two. It's more noticeable in the winter trial, not so much here. And the horizontal gradients exactly the same as what you've seen before, and they all look quite sensible. So I'm just going to flick through these ones quicker so we can focus on the Argo stats later. And then this one is again just to pull out the difference between these two versions of Mu, and then very similar to what we see before. And then we're going to focusing on the Argo observations. So we're looking at time difference of the mean difference to Argo and the standard deviation. And also we're going to have a averaged over the 3 months in terms of regional and global stats. So this one is a very busy plot because I have all the 15, we got 15 lines here. The 11 existing and the 3 new and the GIMP medium. So I'm just going to kind of highlight a couple of them that you might want to focusing on. So the light green is the aviation OI. The Odyssey is in brown. The 2 mil, the full resolution is in yellow. The quarter degree is kind of dark blue, and Austere is dark green, kind of merged in these bunch of lines, and GIMP median is in black. So here for this one, I'm just going to kind of sort of draw a line around about 0.02 or 0.03 negative, and you can see that the aviation OI is the only one that's warmer than Argo. So basically the positive numbers means the analysis is warmer than Argo, and negative means they're colder. And they also match quite well against Argo in terms of magnitude of difference. The next one up is actually MGDST. But most of the analyses are kind of gathering between minus 0.05 and minus 0.10. So for these time periods, Odyssey is actually doing quite well. And Austere is somewhere in the middle, it's about 0.05. Oh, sorry. So this dark brown here is Odyssey. I do apologize. I think the other one is something else. Yeah, so I think between minus 0.05 and 0.1 degree is what we are happy with. This is a kind of normal spread we see. And just to point out, for this time periods, I think the 2 mil version had some problem because based on the longer term analysis stats we have in-house, it does seem like the 2 mils is not doing quite well for this time period. It's a bit unfortunate, but we're going to focus on those two for the summer time periods. And the next one is the standard deviation against Argo. So we tend to think this is a better indication of the quality of analyses. So in these plots, you kind of have maybe 3 groups. The first one is the MGDSST. You have kind of higher anomaly, higher standard deviation against Argo over 0.5 Kelvin, and the better ones will be these bunch that is under 0.4. So we have AWC here, AVHOI here, the GMPE is the bottom, OSTS here. And this is what I meant when the mirror seems to be doing something like it just keep going, increasing from December to February. So I think there is something, they don't usually this high. So I think probably is something problem experiencing in these two analyses. For the summertime, so this time you can see the dark blue line, that's the mirror 0.25, and this time it actually matched quite well with Argo in terms of mean difference. It's a very small difference followed by the AVHOI in the negative side, and MGDSST seems to be quite warm this time. In terms of the other ones we're interested in, so the AWC is around here, so it's slightly over 0.1 negative against Argo, and the full resolution mirror is somewhere here, and the austere and GMPE median was somewhere like 0.05. So the kind of like steady, like that kind of level. In terms of standard deviation, so most of the analyses we are interested in are somewhere between 0.45 to 0.35. So that's kind of level we're seeing. And we can see all the ones we're interested in, the light green here, MHOI, the AWC, which is kind of here. Austere is sort of here, just below 0.4. GMPE median is the lowest, just a little bit over 0.35. So we're kind of quite happy with the performance of all these new analyses, and it kind of bunch up with the existing, most of the existing ones. Obviously, there are always some odd ones here and there, but overall, we're quite happy with the performance. So this one is just a kind of summarize, so the summaries kind of averaged over certain regions. So I chose the global ocean, South Atlantic, and North Pacific. So the North Pacific is because last year we had a discussion where we've noticed the AVHOI seems to be different to many other L4 analyses. That's why we kind of want to focus on this region. And South Atlantic just chose another one, the Southern Hemisphere, but it's not in Pacific. So I highlighted the best performing analyses in bold color. So you can see for the mean difference to Argo, this is for winter periods again. The Argo match really well with match really well with Argo in terms of the mean difference. It shows the smallest difference to the reference Argo. But in terms of standard deviation, it is not bad, but it's so austere seems to be quite well in these time periods and matching quite well with the GMPE median as well. But all the other analyses, apart from this 2 mirror, because they are behind than usually they are, they all kind of performing quite well in the selected regions. This is a similar stats, but for summer. And yes, when mirror is back to the normal status, and you can see it's kind of also performing quite well when comparing against Argo. So the top 3 rows are the mean difference between the analyses to Argo. And so the AVHOI performs quite well in the South Atlantic, and mirror is better in the global and North Pacific. But all of them are performing all right. I mean, in terms of the reference, in terms of the performance in GMPE analyses. And in terms of standard deviation, again, the austere seems to be okay, and the GMPE median, obviously, not surprisingly, have quite good analysis stats. But all the others, there are all between 0.35 to 0.45, so it's acceptable level. Just to have a note about the use of Argo observations in the L4 analyses. So many years ago, there was kind of sort of a it's not like a agreement of sort, but we tend to keep Argo away from L4 analysis in terms of assimilating it into the analysis to keep Argo an independent reference to be used for validation. But there are three products that you have seen just now that assimilate Argo. One is the AVHL-OI, one is the Mu, and the Mu have quarter degree. So I think that probably explains why the AVHL-OI and the Mu, when they're normal, kind of grade quite well against Argo in terms of mean difference. But they don't seem to be significantly better in terms of the standard deviation. So I did think about doing a comparison, like one version of GMPE assimilate only the L4 that does not assimilate Argo compared to the GMPE that assimilates, like use every product. But I felt that's not a better, it's not very good analysis, like comparison, because I can't tell the difference I see is because Argo, or is that because I excluding these couple of analyses? So I think a better assessment of, like pure assessment of how Argo would affect L4 analysis if it's been assimilated would be have a one version, like the same analysis, but one version assimilating Argo, one version doesn't. That's just a thought for discussion. And in terms of GMPE update plan, so we are happy of all the three new analyses. So we're going to include AVHOI in the immediate next system upgrade and Odyssey in the one following, purely because technical reasons, because we're doing the HPC migration and all sorts of stuff. And in terms of Mu, I had a discussion within the ICTT task team. So basically, we decided to keep only the full resolution in GMPE. The main reason is the Mu full resolution has a lot more users, so it's probably make more impact if we have that. And also because the resolution is so fine, so we felt like it might include some information that has been smoothed out by other analyses. So it might be a very valuable asset in the GMPE products. And also because the Mu not quarter degree, I've only heard recently that it's actually being a product from the coverage project, and the project has finished now, and I don't think it's currently running. So we're just concerned about the long-term availability of that. So we decide to, including the full resolution only in GMPE. And the references is at the bottom. So I think that's all my slides. I'm going to leave this one up here, and I'll take questions. Thank you.
Thank you, Chongyuan. We have time for a couple of questions before coffee break. I see one question from Marwan.
Okay.
Hi, Chongyuan. Thanks for your presentation. Sorry if I missed that from your slides. What's the size of the collocation window for the validation statistics?
I don't think we have a fixed one, to be honest with you. So we're just basically seeing the spread, and if it's kind of amongst the, so I'm telling you the 0.45 whatever. So we don't have a fixed one, I think, but generally most of them are between a certain level you can see. So I think probably 0.5 or something. Yeah.
Like, okay.
Is that answer your question?
Yeah, I was assuming that it would be a fixed size collocation window for all the products. Is it being adjusted with respect to the resolution of the original product itself? Like, is it very different for the Muir full resolution and for the Muir quarter degree?
I don't think so. I think we just, I don't think it was an analysis specific. Maybe we should be. Maybe that's a fair comparison, but at the moment, I don't think so. Thank you.
Thanks.
Oh, we have lots of questions in the room. I think that the first one was Andrea.
Hi, Andrea Pisano. Just quick clarification and a question. The clarification, that
I have to hear what you're
ODC.
saying. I'm so sorry. My toddler's next to me. That's why I got distracted.
No problem.
Sorry, Anna. I am so sorry. Sorry.
No problem.
Sorry,
Nice
Andrea.
Well, a quick clarification. I would like to remind that ODC does not substitute Ostia within the Copernicus Marine Service. Both products are currently distributed. And the question is if GMPE is currently operationally produced and distributed.
I'm sorry. The
if GMPE is operationally produced and distributed within the GRIS catalog or somewhere else?
So at the moment, I believe nowhere. So since the end of 2022, I think we're not actually disseminating GMPE anywhere. So I did mention when we kind of thinking about having this UQAM CAS, which is UK-based dissemination service. I did mention about GMPE, but unfortunately at the time they want to focusing on the top priority ones, which being the Ostia and then the Dino products, I think also being on there because it's like not just Met Office wide, so they have other products. I think they want to focusing on the if each of organization only the couple of the top priority ones. So GIMP did not make the cut. But I think the GRIS catalog is definitely a good idea. We probably should kind of investigate that route of disseminating data. So unfortunately, GMPE has been like because we also have in-house Met Office something called Service Hub. I did mention about having that there. With the ones did not make the UK AMCAS, but unfortunately, that one they will have to kind of balance between the marine products and the atmospheric products. And again, this time didn't make the cut, so it's a bit unfortunate. But maybe we would investigate like product or
many thanks.
Yeah, thank you.
We have another question over there. Then Jorge, and yes, please go ahead.
Irina Glasova.
Jorge, wait, we have another question before. I will come for you later.
I'm sorry. Just a quick thank you for that presentation. Just a quick comment on the Mirror 25 versus 1 kilometer. They're both made with exactly the same algorithm. The wavelet coefficients are the same. So basically the 25 kilometer, all it does is it uses those wavelet coefficients to grid them.
Right.
In a different way. So I personally don't think you would be losing by just focusing on the 1 kilometer. I don't think you would be losing any kind of feature resolution that associated here that adds to the. Anyway, just my comments. Thank you so much.
Thank you. Yeah, so I think like losing the 1 kilometer is definitely going to be a bigger impact than losing the 25. So yeah, thank you, Jorge.
Please go ahead.
Second attempt. Irina Glasova, I have a very quick, simple question. So when you select in the median for your ensemble, do you keep track which product is becoming the median? And is it possible to see which product is a main contributor to your median, GMPE ensemble? Because, for example, if there is, let's say, extreme case, one product is completely useless and it's by 10 degrees off, right? It'll never make into the median selection. And it might be that without it, you would be doing much better. So have you performed any sensitivity study of whether any product is not contributing ever and never becoming a median, and removing it would make your GIMP perform better? It's easier to keep growing the ensemble to more and more members, but do they really make any contributions? Basically, my question is with respect to sensitivity study, if you have done any, and share your experience with us.
Yeah, thank you. I think it's a good question. What we have in the kind of normal monitoring web page, we have a plot which using different colors to indicate where, like, which product that particular point comes from. But that's a kind of global map, and it probably, if like a multiple products producing the same grid point or something, it might overlapping. So it's always a very busy plot. You can probably just glance at what color seems to dominate. So I think that's we haven't done something like a very sophisticated sensitive test. Like I can tell you which one dominates. The only thing I think kind of along that line is this map. Well, I haven't included in my presentation, unfortunately, so I can't show you one example now. But essentially, that's the kind of thing that come to mind now. But I think what you said is very correct. We probably should do that. Some of the analysis, just based on looking at the AGO stats, I can see that's always the outlier compared to the majority of analyses. So maybe that might not include a lot of bring a lot of benefits by being included in GIMP. So yeah, so it's definitely a fair question. We can investigate more in the future.
Moreover, if you have one which is an outlier, it will affect your median selection. So yeah, median is very sensitive to the presence of the outlier thing. Just a comment.
Yeah, thank you very much.
Last question before coffee break.
It's hard to say a question, maybe just a comment that in this kind of comparison, I think I agree with the previous question that maybe all these products, because they have different spatial resolution, so maybe it's actually it's fair or it's good to regrid all these data set at the same grid size. Then we do the intercomparison, because our analysis kind of suggest in the previous study that if we do the intercomparison from the original product's grid point interpreted to the in situ grid point, that actually there's some high resolution product, their root mean square error or standard deviation actually is pretty smaller. But if liquid to a kind of low resolution, saying a quarter degree, their actually standard deviation changes a lot. So I think it depends on the resolution. I think the deeper reason is how the bias correction of satellite SST was being done in the analysis. So like take the NCI's example, we do the bias correction. Actually, it's very large using the UF patterns. So basically the largest scale patterns of bias correction. But for some product, maybe they're using the kind of within 50 kilometer to 100 kilometer, like the matchups. So for the small scale, the catch actually is good, but for the larger scale, maybe not as good as UT or UF. So this explains why in the NCEI case, the OISST for the global mean bias actually is small because we're using the larger scale bias correction. But for the standard deviation, actually is not as good because we did the mean bias, but for the small scale, we didn't. So as good as other products.
Yeah, I think that probably explains it. Yeah, thank you.